Now let's do all four fundamental spaces of linear algebra in one video. In previous videos, we defined them and we derived methods for finding their dimension and basis. That's the big things we want to do. Find their dimensions and their bases, a basis. To review, what were those four spaces? The row space, A is the matrix we're talking about. The row space of A, and its dimension was its rank. R is the rank. A is M by N. M rows, N columns. The column space of A, we could also call that the row space of A transpose. Its dimension was the same, the rank of the matrix. So the dimension of the row and column space are the same, they're the rank of the matrix. The null space of A, its dimension was N, the number of columns of A, minus the rank of A. We derived why that's true in previous videos. This video is just about how to calculate things. The null space of A transpose, also called the left null space of A, its dimension is M minus the rank, where M is the number of rows. So the dimensions are easy once you have the rank. How do you find the basis? And we derived all this from previous videos, but I'll summarize it in words first and then do an example. For the row space of A basis is just the non-zero rows of U, where U means after doing row operations, and U is in row echelon form. Column space. A basis is the columns of A that correspond to the pivot columns of U. There'll be the pivot columns, there'll be as many pivot columns as the rank of A and U. The null space of A, you do elimination and you express the pivot variables in terms of the free variables, And then you use the 1-0 trick to flesh out the basis. There aren't any free variables. If matrix A is full rank, then the basis is just the empty set. The dimension of the null space is 0. The left null space, or the null space of A transpose, you can do it two different ways. You could just transpose A and then find the null space of A transpose the same way we found the null space of A. Or the other way, which you would probably do if you're also asked for all this other stuff, so you don't have to do a lot of extra work, you augment the matrix A with the identity when you're doing all that Gaussian elimination. And then the basis will be the rows of E that correspond to the all 0 rows of U. Actually, they're transpose. Well, let's do an example. Here's A, and because we're asked for all 4 spaces, I'll go ahead and augment it with the identity matrix on the right. Same number of rows as A has. So here on the left is A, here on the right is the identity. We do some row operations, and it's pretty quick here. This left side, the A part, got a row of all zeros. There's a pivot, there's a pivot. It satisfies the criteria for row echelon, in fact, strict row echelon form. It's not in reduced row echelon form, but it's in row echelon form. So this left side is what we'll call U. This right side is what we'll call E. And we've got all the dimensions. We did this on the previous chart. The row space is going to be the rank, which is 2. 2 non-zero rows. Column space is also the rank. The null space is n minus r. N is 4, r is 2, so that's 2. Null space of A transpose, or the dimension of the left null space, is m minus r, which is 3 minus 2, which is 1. Now let's find the basis. row space is easy. It comes from U. It's just the non-zero rows of U, or you could call it the pivot rows of U. So these top two rows, that's easy. Okay, there's a pivot, there's a pivot. Only two pivots. It's the left, this left column and this second column. So the basis of the column space is the corresponding columns of A. So 1, 0, 1, 2, 1, 2. This told you what columns to use. And we get the columns from A. The null space. This is just in row echelon form, not reduced row echelon form. What this top row means is x1 plus 2x2 plus x4 equals 0. This second row means x2 plus x3 equals 0. Because we didn't go full Gauss-Jordan, we got to do a little extra algebra here. So I'll set x2 is a pivot variable. We want all the pivot variables in terms of all the free variables. And this tells us x1 and x2 are the pivot variables, and then x3 and x4 are the free variables. So anyway, from the second equation, we get x2 equals minus x3. Then we can substitute that back here, and we have everything in terms of only the free variables. Or we have pivot variables only in terms of the free variables. At this point, we use the 1, 0 trick. We'll first set x3 to 1 and x4 to 0. x3 is 1, x4 is 0. And then let's see, x1 equals 2. And x2 equals minus 1. For the second one, we set x3 to 0 and x4 to 1. x3 is 0, x4 is 1, x1 is then minus 1, and x2 is 0. So there we go. That's the basis for the null space. There's one left. Whoops, if we solve it from scratch, we just transpose A and find its null space. This is a different view from before. I won't go through that one. It's just doing the null space all over again. But since we went through the trouble of augmenting the matrix and finding E, let's do it that second way. Here's U. It's got a row of all zeros, just one. The corresponding row of E is minus 1, 0, 1. So its dimension is just 1. We already calculated that. I only need the one vector. And it's just the transpose of this row of E that corresponds to the all zero row of U. There's the complete example, all four spaces. And we stop it there.